Hello, welcome to the 7th section, Decision Trees and Ensemble Learning. We start off this section with the video Binary Decision Trees, which deals with the introduction to binary trees. Up next is Decision Tree Classification, and in the last video we'll learn about Ensemble Learning. Now we move on to the first video, Binary Decision Tree. In this video we're going to take a look at binary decisions, impurity measures and feature importance. A binary decision tree is a structure based on a sequential decision process. Starting from the root, a feature is evaluated, and one of the two branches is selected. This procedure is repeated until a final leaf is reached, which normally represents the classification target we're looking for. Considering other algorithms, decision trees seem to be simpler in their dynamics. However, if the data set is splittable while keeping an internal balance, the overall process is intuitive and rather fast in its predictions. Moreover, decision trees can work efficiently with unnormalized datasets because their internal structure is not influenced by the values assumed by each feature. The decision tree always achieves a score close to 1.0, while the logistic regression has an average slightly greater than 0.6. However, without proper limitations, a decision tree could potentially grow until a single sample is present in every node. This situation drives to overfit the model, and the tree becomes unable to generalize correctly. We'll now learn about binary decisions. Consider an input dataset X. Every vector is made up of m features, so each of them can be a good candidate to create a node based on the feature threshold tuple as shown. According to the feature and the threshold, the structure of the tree will change. Intuitively, we should pick the feature that best separates our data. In other words, a perfect separating feature will be present only in a node, and the two subsequent branches won't be based on it anymore. For example, let's consider a class of students where all males have dark hair and all females have blonde hair, while both subsets have samples of different sizes. If our task is to determine the composition of the class, we can start with this subdivision. However, this block, dark color, will contain both males and females, as these are the targets we want to classify. This concept is expressed using the term purity. An ideal scenario is based on nodes where the impurity is null, so that all subsequent decisions will be taken only on the remaining features. In our example, we can simply start from the color block. The two resulting sets are now pure according to the color feature, and this can be enough for our task. If we need further details, such as hair length, other nodes must be added. More formally, suppose we define the selection tuple as shown. Here, the first element is the index of the feature we want to use to split our dataset at a certain node, while the second is the threshold that determines left and right branches. The goal is to reduce the residual impurity in the least number of splits so as to have a very short decision path between the sample data and the classification result. We can also define a total impurity measure by considering the two branches. Here, D is the whole dataset at the selected node. D left and D right are the resulting subsets, by applying the selection tuple, and the I are impurity measures. Next we'll look at the Gini impurity index. The Gini impurity index is defined as, here the sum is always extended to all classes. This is a very common measure and it's used as a default value by Scikit-learn. Given a sample, the Gini impurity measures the probability of a misclassification if a label is randomly chosen using the probability distribution of the branch. The index reaches its minimum, 0.0, when all the samples of a node are classified into a single category. Next, we'll learn about Cross-Entropy impurity index. This is how the cross-entropy measure is defined. This measure is based on information theory and assumes null values only when samples belonging to a single class are present in a split, while it's maximum when there's a uniform distribution among classes. When growing a tree, we start by selecting the split that provides the highest information gain and proceed until one of these conditions is verified. All nodes are pure. The information gain is null. The maximum depth has been reached. Next, we'll look at Misclassification impurity index. The misclassification impurity is the simplest index and is defined as, in terms of quality performance, this index is not the best choice because it's not particularly sensitive to different probability distributions. Now we'll look at feature importance. When growing a decision tree with a multi-dimensional dataset, it can be useful to evaluate the importance of each feature in predicting the output values. Decision trees offer a different approach based on the impurity reduction determined by every single feature. In particular, considering a feature xi, its importance can be determined as the sum is extended to all nodes where xi is used, and nk is the number of samples reaching the node k. Therefore, the importance is a weighted sum of all impurity reductions computed, considering only the nodes where the feature is used to split them. If the Gini impurity index is adopted, this measure is also called Gini importance. So, you've learned the basics of decision trees.